Today we'll be focusing on how to write some code to control servos through an Arduino. Now the first step we want to do is to consider the setup. This is run at the beginning of the program, mainly for setting up. Now before we do setup specifically, we want to declare two main arrays. We want a way to store the pins corresponding to each servo, and we can represent each servo pin as an integer, and all the servo pins together as an array. We have 5 servos of interest, so we can declare the array to be of length 5, and the pins in question are 9, 6, 5, 3, and 11. This is just going off of what pins the servos are connected to on the Arduino board. The next step that we'd like to do is to also have a way of representing the state of each servo at any given time. Similarly to the pins, we can represent each state as an integer, all the states together as an array. Let's call this servo states. And since we have 5 servos of interest, we can have the array be of length 5. Now, we can take a look at the setup. In the setup, we want to be able to communicate with the Arduino using the serial monitor. So we can say serial.begin and select the baud rate to communicate with. For our example, we'll set the baud rate to 74880. We can also set the timeout using serial set timeout, and let's set it to 2 for the time being. Now we declared our servo pins and our servo states before our setup. We'd now like to actually initialize our servo states. So we want to be able to go through each of the servos. We can do so by introducing I, an index, and we want to have I go through all the possible indices of our arrays, where our arrays are 0 index, going from 0 all the way to 4. And inside a loop, we want to say for the ith servo, we want its state to be initialized to be 0, and we also want to declare its pin as an output pin. We can use the pin mode function to do so. The servo pin of interest of the ith servo is servo pins I, and we want to declare it to be an output pin. Once we have completed doing so for all of our servos, we can now say we want some output from our Arduino. We can have it print out something to the serial monitor that will tell us setup has completed. Let's have it say hello world. So in our program, in the beginning, it will start the baud rate at 74880. It will set the timeout. It will initialize all the servo states to be 0 and declare all of the servo pins that we have up above to be output pins. Finally, it will print hello world once setup has completed. Now let's try uploading this to our board. And in our serial monitor, here you can see that hello world is printed out. This tells us that setup has successfully completed. Now that we have written the setup, we can now take a look at the rest of the code that we'd like to write. You can see the loop function. This is going to be run repeatedly after setup has completed. Now, since we're interested in writing code for the servos themselves, let's define a few main functions for what we'd like them to do. We want a function that will go through all the servos, that will then run the servos for however long each one needs. And this is dependent on the angle, aka their state that we are storing in servo states. And this will be the general logic that we have. We can define a function called void, which means it doesn't return anything, and call it run duty cycle. It also doesn't need to take in any parameters since we're just dealing with the servo states and the servo pins defined in the beginning of the code. Now in run duty cycle, we'll likely also need some utility functions. Some utility functions for run duty cycle. We need to be able to figure out for a servo, given its angle that we want it to be at, how long should the servo wait? So let's define a function that returns an integer. This integer should represent how long the servo should wait. Let's call it time to wait for a given servo. And we want the input to this function to be the angle at which we want the servo to move to. So let's have the angle be represented by an integer and call it angle. Now we can implement this by recognizing that the min time to wait for a servo will be 544, and the max time to wait for a servo should be 2400. And the possible angles that a servo can have ranges from 0, which corresponds to 544, and all the way to 180 degrees, which corresponds to 2400 in terms of how long the servo should wait. In that case, we can return the value of the formula, 544, plus our angle times the difference we need to get from the min to the max divided by 180 degrees. So in this case, if the angle is 0, time to wait will return 544. If the angle is at 180 degrees, time to wait will return 2400. And the min and max times to wait here are just from how servos are made. So we have this utility function time to wait. This tells us, given some angle, how long a servo should wait for. Now, another thing that might be helpful is in run duty cycle where you want to go through every single servo, but each servo might have different angles that they need to be at. And as a result, some servos might run longer than others. So what we want to do is to have a way at any one time to take a look at all of the times to wait remaining for each of the servos and see what is the minimum time to wait remaining. And the way we can represent remaining, we can represent the time we've already waited as a threshold. To start off with, let's say that we want to create this function. We want to return the value that is the minimum time to wait from the time we've already waited to the next time that we should stop and do an action, aka when a servo's time to wait has ended. So let's call this min greater than. What we want to take in for this function is the array in question. So let's make this array called ARR, short for array, an integer that represents the length of the array, as well as an integer that represents the threshold. Remember, this threshold is going to represent the time that we've already waited. Now, let's let's check for a few things. We want to return some value. Let's call this val to begin with. And we want to go through the entirety of this array. So for that, we can use a for loop, similar to what we did in the setup. Again, we can introduce a variable I to represent the index as we're going through this array. Now we want to go through the entirety of the array, so we say continue on with this loop until I has reached the length of the array, aka no longer a valid index, and continue incrementing if not. Now in this case, we must first check, has this element in the array at array index I, is it greater than the threshold that we are interested in? If it's not greater, then we don't want to consider it. So let's say if this is true, so if the array element is greater than the threshold that we've already waited, then we want to check a few things. We want to say, well, if we've already found the value, then we should say the value should be updated to be the minimum of the value we found previously and the current array value. For example, if our array held 3 and then 1, where our threshold is 0, we would find 3 to be minimal when we were at 3, but once we reach 1, we would find 1 to be minimal. So that is the case that we're interested in. Otherwise, we can say that we haven't actually found a value that has been greater than the threshold yet. So we want to set value to the array element directly. Now the way we can represent whether we found a min value or not is through using a boolean. Let's define this boolean to be called found. Bool found false. That means we haven't found anything in the beginning. But if we've already found something before, then it's fine to compare the previous value we found with the current value that might also be a candidate. Once this for loop is done, we then want to check. We want to say if we had successfully found the variable, then we can return value directly, since we know it will have a meaningful value. Otherwise, we can return -1. So here we're assuming that all of the values in the array are greater than 0, which greater than -1, which will be true since in our case 544 to 2400 will be all of the possible values in our array, but this is just one thing to note. As a side note, another way we can write this if-else expression is using a ternary expression, such as saying, instead of having to write all these lines of code, we can instead write something like return value if found is true, otherwise return -1. So if found is true, return value, otherwise return -1. So let's look at what we've written so far. We've written a utility function for run duty cycle called time to wait. This takes in an angle and it returns the number of time that we should wait for our servo. If the angle is 0, we should wait 544, otherwise we should wait 2400. We also introduced another utility function called min greater than, and this will be helpful in terms of figuring out when we're going through all the servos, how much longer should we wait, and then figure out whether to take an action of a servo or not. In other words, when we want to figure out in our array, have we reached the point yet about how much longer we need to wait until one servo no longer needs to wait anymore, based on time to wait. Now that we've written the utility functions we will use, we can now take a look at how we can write our code for a run duty cycle, which will again go through all of the servos and run the servos for however long each one needs. The first thing we'd like to do is to define an array of wait times. We can represent each time with an integer and define the series of wait times for each servo as wait times. Since there are 5 servos, we can make our array be of length 5. We would like to initialize this array. We can do so by using a for loop, where we can define I to be the index, have I continue along in our loop until we've reached the end of the array, and if we have not yet reached the end of the array, have I increment to the next index. Now inside of our for loop, we would like to figure out what exactly is the time that we need to wait for this specific servo. The servo that we are interested in wants to go to servo states I. This will represent the angle at which we want it to be at. We can pass this angle into our utility function time to wait. Now time to wait will take in this angle and return us how much time this servo specifically needs to wait. We can now store it into our array at wait times for the ith servo. The next thing we would like to do is when we say run the servos for however long, this means we would like the servo pin to be high for wait times I amount of time, and after that time to wait has been reached for the ith servo, we would like to turn the ith servo from high to low. But first we need to turn the servo to high. We can use digital write as a function that takes in the servo pin for the ith servo and then sets it to high. The next thing we would like to do is we want to be able to go through all of the servos, turn off each servo at the time that it needs to be turned off, and to do that we can introduce 2 helper variables. One will be min delay, which is 0, which says that from one step to the next, we can never have a negative amount of time that we need to sleep. And the next helper variable that we will introduce will be cur, short for current. Now this current variable will represent the amount of time that we've already waited. We can now introduce a loop. Now our goal for this loop will be that we want to continue in this loop until all servos have been turned from high to low. To start off with, let's figure out how much time we need to wait from the current time, where we've just turned all of the servo pins to high, to the next time at which we need to turn at least one servo to low. Let's define this to be next cur. Here we can use the second utility function that we defined, min greater than. This utility function, remember, takes in an array of times, the length of the array, and finally the threshold. Wait times will represent the array of interest. We know that wait times has length 5, the way we declared it. And the current threshold should be current, because that's how much time we've waited so far. With this, we should also check if next cur is equal to -1. if you recall from min greater than, it will equal -1 if there are no elements in our array that are greater than cur. So in this case, that means all servos have been set to low. We have no more time to sleep, no more time needed to sleep, and so we can break from our loop. Before that happens, however, if we still have some time to sleep, then we will continue and not break. Now we have to figure out how much time we actually need to sleep. Let's call this sleep time. We can define it to be next cur minus the current time, which we've waited. Why is this the difference? Because min greater than will return the element and not the difference. So if next cur is 6 and cur is 2, we expect the sleep time to be 4. Now we also want to acknowledge the fact that what if this is negative? We can't sleep a negative amount of time. And so we should say, turn this into a max statement and say either we sleep 0 if next cur minus cur is negative, or we sleep that difference. We then want to delay microseconds the sleep time that we have. So this will mean that when we call delay microseconds, when sleep time is 4 microseconds will pass before we continue on in our program. Once this has completed, we want to update our current. Remember, current stands for how much time has already passed over the course of this section. We would like to increment it by sleep time since we've slept that amount of time. And we now want to check, if we have indeed reached the time for our servo to be turned off according to its wait times, we should turn it to low. Let's use a for loop for this. We can introduce I to be our index. As long as I is less than 5, the length of our array, we can continue incrementing, and we want to check if the wait times for the ith servo, if it's less than our current time, then we should say we've already waited enough time for this servo. We can now set the servo to be low. So digital write, once again it takes in the pin for the ith servo, but instead of high we want it to set it to low. Finally, at the end, once we have turned all servos off from high to low, and next cur is equal to -1, and we've broken from the while loop, we can delay a few more microseconds. For example, we can say 4,000 microseconds minus the time that has already passed, and this means that every run of the run duty cycle lasts 4,000 microseconds. This is just to give us some buffer room in between when we run this periodically. Now that we've defined our run duty cycle, we can now go to the main loop. Inside of our loop, what we want to do is we want to run our run duty cycle every single time. So let's do that first. Run duty cycle. We can call it in our loop as follows. And now let's try and see what happens when we upload this code. We can first run a verify step that will compile it to check for any errors in terms of compilation. Looks like there were none. We can now upload this to our robotic arm. And if we go to the serial port, we can see that hello world has been printed a second time, since this is the second time that we've uploaded. We can also see that the robot arm is now in the 000 position. As a quick example, let's see what happens if we go back to our setup. Here we initialize every servo state to be at the 0 position. What if instead we change it to the 30 degree angle position instead? Let's try uploading this. Now this is done uploading. You can see hello world is printed a third time. That means setup has completed. And the robotic arm is now initialized in the 30, 30, 30, 30 position, where all of the 5 servos are at degree 30. Okay, let's set this back to 0. Now we would like to introduce some interactivity with this. We've seen that the servos can all hold their positions. We can now figure out whether we can give some input to the Arduino to change the positions of the servos without having to upload a new sketch to the Arduino every time. So let's take a look. Before we run and call run duty cycle, let's have our Arduino do the following. We wanted to check, is there any input that we are giving to it? We can use the function called serial available. If serial available is greater than 0, that means we have typed something into our serial monitor, for example. Now, let's say we want to give the command that looks like the following. Command into the serial monitor, something like 0, 50. Let's have this first one. Let's have the first integer should represent the index of the servo we want to move. So the 0th index will represent the 0th servo, the 4th index will represent the last servo. The second integer can represent the angle of the servo we want to move it to. So in this case, the angle that we want to move the 0th servo to should be 50 degrees. In order to parse this, we could use the libraries that are available. In the serial library, we have the parseInt function. Now serial parseInt called once will give us the first integer that was typed. So let's define that to be the servo index, and serial.parseInt, when called a second time, will give us the second integer, which we will have representing the servo angle. With these two, we can now set the servo states. We want to set the servo index corresponding to the servo in the servo states. We want to set its state to servo angle. Now this by itself won't yet move it immediately, but when we make this change, it will affect our run duty cycle call, which refers to the servo states array in order to figure out what angle to move each servo to. To get some more feedback, let's also have the Arduino print out what it has parsed. So it can first print out the servo index. Let's have it also print out a space, and finally print the angle as well as a new line to help us better distinguish between different commands. Now, what this loop does is it will first check, is there any input available? Is serial available greater than 0? If so, that means we would have typed a command into the serial monitor. Our command should look like the following: 2 integers, the first representing the servo index, the second representing the servo angle. Our code will then set the servo state for the servo corresponding to the given index to the given angle. The Arduino will then print to the serial monitor what command it has received, and then run duty cycle will be executed, which will move the servos to how we would like them to move to. So let's try uploading this sketch to our board. It's done uploading. If we check our serial monitor, we'll see that Hello World has been printed a fourth time. This is how many times we've uploaded our sketch. And now we can actually type commands. For example, if I type 00 and send my command, 00 will be printed out. However, there is no change since the 0 servo is already at the 0 position. Now let me try for the servo at servo index 1. What if I send it to the 30-degree position? You can see that here the robot has moved. Now let's try 150 or 160 or 170, and we can see that it has been moved to that position. Now for the sake of this video, why don't we try moving the arm to look straight up. We can say for the servo at index 2, let's move it to the 30-degree position or the 50-degree position or the 90-degree position. We can also take a look at the third index. So index 3, let's move it to the 60-degree position, which rotates as such. And finally, we can try opening the claws of the robot arm. So this is index 4, and let's have it go to degree 25 degrees. And it opens, and at 0 degrees, it closes again. So here you can see that the code that we've written now allows us to interact with the robot arm. This is the code that we wrote, the main loop, which has information about interactivity, as well as calling run duty cycle itself, which takes care of the main logic of moving each servo to where we want it to go, and some utility functions min greater than and time to wait, which we use in our run duty cycle to help the servos go to where they need to go. And if you remember all the way back to the beginning of this video, we also defined a setup function, which ran at the very beginning of the code, was in charge of initializing the servos to be at 0 degrees, and declared each of the pins for the servos to be an output pin. Thank you for watching, and hope you learned more about how to write code for Arduinos to move servos around.